Welcome back to the deep dive. Today, we are stripping vision back to its absolute mathematical studs.
hmm
We take it for granted, right? You look at a coffee mug, you know it's a cylinder, you know it's 3 feet away.
hmm
But for a computer, looking at a flat grid of pixels and trying to hallucinate a rich, solid 3D reality from it.
It is a nightmare of ambiguity. It
Yeah.
really is. It's the fundamental reverse engineering problem. You have this 2D map and you're trying to build a 3D territory from it.
And the math just collapses.
A lot of the time, yeah.
And that's what we're tackling. We're looking at a seminal dissertation from 1993 by Robert T. Collins titled Model Acquisition Using Stochastic Projective Geometry.
Which is quite a mouthful.
It is. Stochastic projective geometry sounds incredibly dense.
It sounds like jargon.
But essentially, Collins is arguing that for decades, engineers were forcing computers to look at the world through the wrong mathematical lens. You're trying to force a round world onto a flat sheet of paper and then acting surprised when the numbers just blew up.
That's a great way to put it. He realized that the tools we were using, standard statistics, the things you learn in Intro to Stats, were actually incompatible with the geometry of how light enters a camera.
So the mission today is to understand why that flat math fails
Mhm.
and how moving everything onto the surface of a sphere, literally wrapping the math around a ball, solves the problem of infinity.
And how it lets robots see things with a precision that was, essentially unheard of at the time.
Let's start with the villain of the story, the bell curve, the Gaussian distribution. We see this everywhere.
Everywhere. It is the bread and butter of handling error. Because sensors are noisy, right? The pixel is never perfectly placed, there's always jitter. So you use a bell curve to say the point is probably here, but it might be a little over there.
The standard mountain shape.
Yeah.
Most likely in the middle, less likely at the edges.
Correct. But the Gaussian distribution assumes you are operating on a flat, infinite plane Euclidean space. If you walk in one direction, you can just keep walking forever, and the math holds up.
It assumes the world is an infinite sheet of graph paper,
Exactly.
which seems fine. I mean, photographs are flat, they're rectangles.
Yeah.
Why doesn't flat math work on a flat photo?
Because the content of the photo isn't flat, vision is projective. Think about the classic art class example, railroad tracks. In the real world, those tracks are parallel.
They never touch.
But in a photograph,
They converge, they meet at the horizon.
exactly, they meet at a vanishing point. Now, geometrically, that vanishing point represents infinity. It is where parallel lines meet. In the real world, you can never reach it. But on the image, it's right there. It's a specific pixel you can point to.
Oh, I see where this is going. If I try to apply standard math to that point,
The math explodes. If you use standard coordinates, Cartesian x and y, how do you write down the coordinates of a point at infinity? You can't. It's undefined. And if you try to calculate error bars around infinity using a flat bell curve, the computer just crashes. You are effectively dividing by zero.
so the flat map works fine for the coffee mug on the table. But the moment you look at the horizon, the system breaks.
Precisely. And in computer vision, you are constantly dealing with these singularities. Collins realized that if we want robust vision, we need a geometry that treats infinity just like any other point. No special cases, no crashes.
And this is where he pivots to the pinhole camera model. Walk us through that, because this seems to be the foundation of his fix.
Sure, so imagine the simplest camera possible. A black box with a tiny pinhole. Light rays from the outside world pass through that pinhole and hit the back of the box to form an image.
Simple enough.
Now, usually we describe the spot where the light hits. We say pixel at coordinate 10, 20. But Collins says, don't think about the spot, think about the ray.
The beam of light itself.
Right. That entire line of sight stretching from the camera through the pinhole out to the object. In mathematics, we call this using homogeneous coordinates. Instead of defining a point by where it lands on the paper, we define it as a vector, a direction pointing out from the camera.
So every pixel is basically an arrow pointing into space.
Yes. And this is the aha moment. If you treat vision as a bundle of arrows pointing out from a center, what shape do you get if you cap all those arrows?
A sphere. You're looking out in all directions.
Exactly. The unit sphere. Collins argues that the natural home for vision data isn't a flat plane, it's the surface of a sphere surrounding the camera.
Okay, but does that actually solve the railroad track problem? You still have the horizon.
It solves it beautifully. On a flat map, infinity is off the edge. You fall off the table. On a sphere, infinity is just the equator.
It wraps around.
It wraps around. If you follow the railroad tracks on the sphere, they simply converge at a point on the equator of vision. It's a valid coordinatable location. You can do math there. You can calculate errors there. Nothing explodes.
That's a really helpful visualization. It turns an infinite broken table into a closed, safe loop. But there was a weird detail in the notes here about antipodal points.
Ah, yes. This is the trickiest part to wrap your head around, but it's crucial.
Antipodal means opposite, right? Like the North and South Pole.
Correct. Now, remember our light ray. It goes through the pinhole. But geometrically, a line extends infinitely in both directions. It goes out to the object, but if you trace it backwards, it goes out the back of the camera too.
Okay.
So that single line hits the sphere in two places. The front, the North Pole, and the back, the South Pole. Collins math treats these 2 points as equivalent. They represent the same line.
Wait, so the North Pole is the South Pole?
In this specific geometric framework, yes. It creates a topology where there are absolutely no edges. If you walk past the North Pole, you don't start going down the other side. You are essentially instantly at the South Pole coming up.
Okay.
It's weird, but it makes the space compact.
Compact meaning manageable.
Meaning contained. Standard statistics needs a contained space to work properly. By gluing the opposite sides of the sphere together, mathematically speaking, you create a perfect playground for probability.
Which brings us to the stochastic part of the title. If we are now living on this weird, glued-together sphere, we can't use the standard bell curve anymore, Ron.
Yep.
A bell curve is flat. You can't wrap a flat sheet of paper around a ball without crinkling it.
Exactly. The crinkles are where the errors happen. So Collins says, throw out the Gaussian. We need a probability distribution that lives on the sphere.
And he proposes Bingham's distribution.
Bingham's distribution.
I'm going to go out on a limb and say most people, even engineers, might not have used this often.
It's definitely more niche. It was developed by Christopher Bingham in 1974. Think of it as the bell curve's spherical cousin.
How does it look different?
Well, remember the antipodal thing. North equals south. Bingham's distribution respects that. If there is a hot spot of probability at the North Pole, there is an identical symmetric hot spot at the South Pole. It mirrors itself.
So it handles the geometry correctly.
Mm.
But does it give us anything else? Or is it just correct?
Oh, it gives us something incredibly powerful. Shape flexibility. A standard Gaussian is just a blob, a circle or an oval. But Bingham's distribution on a sphere can look like a tight dot, or it can stretch all the way around the sphere like a band.
A band. Like a stripe on a beach ball.
Yes. And this is vital. Imagine you see a line in an image. You know the object is somewhere along that line of sight, but you don't know where. That is a great circle on the sphere. Bingham's distribution can represent that specific type of uncertainty. I know the line, but not the point. Purely mathematically.
So it's an uncertainty calculus that can speak the language of lines, points, and planes fluently without trying to approximate them as dots.
Bingo! It captures the structure of the error, not just the amount.
Okay, the theory is elegant. Spheres, wrapping, weird mirror distributions. But Collins was an engineer. He wanted to build things.
He did, and the dissertation is full of these really rigorous experiments to prove that this isn't just philosophy.
The first one that caught my eye was the vanishing point analysis. We talked about railroad tracks. But he used this to analyze aerial photos of industrial sites, right?
Right. He used the Radius Model Board 1. It was a highly detailed 1.500 scale model of buildings. The goal was to look at a photo, find the edges of the roofs, and figure out the orientation of the buildings by finding where those lines converged.
And this is hard because roof lines are often short. And parallel lines in photos can be messy.
Very messy. If the lines are almost parallel, the intersection point is miles away or at infinity. Conventional algorithms try to average these intersection points. But imagine this. One pair of lines meets at positive infinity. A slightly noisy pair next to it meets at negative infinity.
If you average positive and negative infinity.
You get zero, or garbage. The average of those two huge errors is a meaningless point in the center of the image.
Ouch. But on the sphere.
On the sphere, positive infinity and negative infinity are the same point. They're just the equator, so the average is the equator. It gives you the correct answer.
That is such a satisfying fix.
It is, and he found something else really interesting here regarding structural versus functional modeling.
Yeah, break that down. What's the difference?
The structural model treats every line it sees as an equal vote. I see a line, I count it. The functional model weights the data based on quality.
And in computer vision, quality usually means length.
Exactly. A long line across the image has way more pixels. It averages out its own noise. A short line, like a chimney edge, is just a few pixels. It's jittery.
So the functional model tells the math, trust the long lines more.
And because he was using Bingham's distribution, he could bake that trust directly into the math. The result. He got the orientation of these buildings correct to within 2.3 to 2.7 degrees.
For 1993, that feels incredibly precise.
It's construction grade. It proved that respecting the geometry pays off in accuracy. It showed that the functional model was vastly superior simply because it handled the uncertainty better.
Okay, moving from single photos to stereo vision. Two eyes. Stereo line correspondence.
This is one of my favorite parts of the paper. Traditionally, stereo vision is all about point matching. Find a corner here, find the same corner there, triangulate.
But Collins says, forget points, look at lines.
And looking at lines leads to a counterintuitive discovery. He showed that you can figure out the 3D orientation of a line, which way it's pointing in space, without knowing how far away it is.
That doesn't sound right. Don't you need depth to know orientation? If I see a line, it could be a small line close up or a huge line far away.
For size, yes.
Okay.
But for orientation, no. Not if you use the sphere. Imagine two cameras looking at a line. Each camera defines a plane that cuts through its own sphere. Where those two planes intersect, that defines the 3D line.
So you can uncouple the what angle is this problem from the where is this problem.
Exactly. And that simplifies the math enormously. He tested this in a hallway. The hallway example.
Classic robot testing graph, lots of straight lines.
Right. He took stereo images looking down a corridor. Now, to a standard computer, that's just a soup of edges. But Collins' system mapped all those lines onto the sphere and looked for clusters.
And it found the walls.
It grouped the lines into three distinct planes: the left wall, the right wall, and a far section of the left wall. It calculated the angle between the walls at 89.4 degrees.
Almost perfectly perpendicular.
But here's the kicker. There were two sections of the left wall. They were parallel, but one was recessed slightly. One was 146 inches away, the other 155 inches.
Less than a foot of difference.
And the system successfully separated them. It knew they had the same orientation. The peaks on the sphere were aligned, but the depth data formed two distinct clusters. This is the power of that uncertainty calculus.
So the computer can reason. I know these are parallel, but I am 90% sure they are different depths.
It feels like the computer is starting to understand the architecture of the room rather than just crunching numbers. It's moving from signal processing to scene understanding.
Which leads us to the final, and maybe most cinematic application, the planar model extension, or as I like to call it, the flying carpet.
Or simply mosaics.
Right. The idea is stitching images together. He used aerial photos of Fort Hood, Texas.
This brings in the concept of homography, a great word.
Define it for us.
A homography is the math that allows you to unwarp a plane. If you look at a rug from an angle, it looks like a trapezoid. A homography stretches it back into a rectangle.
And Collins had a top-down view and a side view of the base.
Yes. A nadir view, which is top-down, and an oblique view from the side. Usually, fusing these is a nightmare because the perspectives are so different. The pixels don't line up at all.
But using his spherical framework,
He could propagate the error correctly. He could predict exactly where a point in the side view should be in the top view, along with a search zone defined by that Bingham distribution.
so instead of searching the whole image, the computer just looks in the tiny oval where the math says the point must be.
Exactly. It makes the matching incredibly efficient. But the real stress test was the PMA robot.
The robot arm, paint the picture.
They mounted a camera on a robot arm and had it rotate. It took 20 images, shifting just 4 degrees between each one. A slow panoramic sweep.
And the robot is trying to build a map of the floor as it moves.
It's doing model extension. It starts with a few points it knows. It turns. It predicts where those points are now. It finds them. It refines its position. It adds new points. It turns again.
This is recursive. If you have a tiny error in step 1, by step 20, you should be totally lost.
In flat math, yes, the errors compound. You drift. But Collins found that the error in locating points on the floor remained at about 0.03 feet.
0.03 feet. That is, what, a centimeter?
Roughly a centimeter, after a full sequence of movement. That is the proof in the pudding. When you respect the geometry, when you accept that the world is a sphere and infinity wraps around, your errors don't snowball. They cancel out.
It's so compelling because it's not about faster chips or better cameras. It's about better philosophy. It's about admitting that the coordinate system we use for drawing graphs in high school isn't the one we use to see the world.
That's the core lesson. We try to force the world to fit our simple tools. Collins built a new tool to fit the complex world.
So, zooming out, this is 1993. Obviously, computer vision has exploded since then. We have self-driving cars, face AI, drones. Is this spherical math still lurking in the code?
Absolutely. The terminology might have shifted. We talk about SLAM, simultaneous localization and mapping now, but the core realization that you must handle projective geometry and singularities robustly, that is fundamental. You cannot build a self-driving car on flat earth math.
It will crash at the horizon.
Exactly. It's that uncertainty calculus that matters. Knowing how wrong you might be and in what direction is often more important than the measurement itself.
I want to leave the listener with a thought that occurred to me while reading this. We've been talking about how to make computers see like humans,
Hmm.
but it makes me wonder about our own brains. We don't perceive the world as a grid of X, Y, and Z. When we look down that hallway, we don't calculate coordinates. Do you think our brains are running something like Bingham's distribution? Are we mapping our visual field onto an internal sphere?
It's a fascinating hypothesis. I mean, evolution is the ultimate optimizer. If spherical geometry is the most efficient, robust way to process visual data without crashing, it would make total sense if biology got there a few million years before Robert Collins did.
So the next time you look at the horizon and see those railroad tracks meet, just remember, you aren't seeing the end of the world. You're just seeing the equator of your own personal sphere.
That is a trippy thought.
Huge thanks to the work of Robert T. Collins for giving us this window into the math of sight. And thank you to all of you for listening.
See you next time.
This has been The Deep Dive.